I am Mr. Tarou. In this chapter of pre-calculus, we're moving into solving linear systems of equations. Initially, and we're going to be doing a lot of this by hand at first, where we're solving two equations with two unknowns and three equations with three unknowns. Now, we've been solving two equations with two unknowns for quite a while now, since Algebra 1. That's finding out where two lines intersect. And indeed, if you're trying to find an intersection point between two lines, there's not necessarily an answer. Those two lines may be parallel. Now, if you start working with three variables and three unknowns, now you start talking about three-dimensional space, and a lot of times we'll be finding out where three planes intersect. Those planes can be parallel, they can intersect in three unique lines, which is both going to be examples or settings of no solution. Those planes could intersect in a single line. That'll be a setting of many solutions, or we can have a scenario where the three planes are all at different angles and they're intersecting at a unique point in three-dimensional space. Now, in this chapter, we're also going to be doing a few application problems, and some of those examples may be something like a parabola, an ellipse, or a circle passes through three coordinates. These are the coordinates. What is the equation of that conic section? And we'll be looking at some applications that don't necessarily seem like they're just three planes in space intersecting at a unique point. But again, and I wanted to show you these diagrams, that when you are dealing with three variables and three unknowns, or three unknowns and three equations, you can have one solution, many solutions, or no solution. So let's get into our first examples for this video and see what we have. Now, in this video, our systems of equations where we have three variables and three equations, or three unknowns, we're going to be solving them with the elimination method. There are going to be in later videos, we're going to learn much more efficient ways of solving for these basically three equations and three unknown systems, these systems of equations, that are a lot more efficient than this elimination process. But we don't want to be completely reliant on technology all the time to solve our problems. So we're going to do this method first, do some applications, and there's two examples I'm going to do today. These planes are going to intersect in a singular point. There's not going to be any examples where there are no solutions or the planes intersect in a line. What we're going to do in the elimination process is reduce the system of where we have three equations and three unknowns. We're going to reduce that to be two equations and two variables. You'll do this by adding two different pairs of equations, and you are probably going to need to use multiplication to either one or both of those two original equations you're about to add to create opposite coefficients in front of the variables or a variable that you wish to get rid of. You'll look at the system, there'll be probably an x, y, and z variable. You'll decide which of those three are most convenient to get rid of, based on the numbers, the coefficients that are in your problem. Use multiplication to create those opposite numbers and add, again, two different pairs of equations to get that one variable gone, and you'll have two equations left with two unknowns. Maybe you'll just have x and y left in both equations, or y and z left in both equations. You'll solve that linear system that you now have been left with after doing step one. You can do substitution, linear combination, whatever you like, but you're going to be left with two variables and two equations. So just a linear system, and solve for one of those variables in any method you like. And then you'll start back substituting. So after step two, maybe you know that z is equal to 2. So you'll take that z value of 2 and then go back up to your 2 by 2 system and plug that variable into one of those equations and find the second unknown variable. And then finally, you're going to finish by taking the two values that you now know, plugging them back into one of the original three equations, and find the last remaining third variable. And we are talking about three variables, x, y, and z. So as my previous introductory screen showed, we are dealing with math now in a three-dimensional space where you have an x, a y, and a z axis. And then, of course, as always, we want to take our numbers, plug them back into one of the original problems, and check our work to make sure that we actually have a valid answer. So let's get one of those first examples started. So here's our first example. These 3 by 3 problems are very long and offer many opportunities to make some careless mistakes, add 2 and 2 and get 5 and so on. So be very, very careful with your signs, and you'll even see me really double checking my work as I go, because you could spend half a page of your notebook paper working these problems out and then ultimately get the wrong answer because you've carried on a mistake through many, many different steps of your problem. So I've got my 3 variables, or my systems of equations up here with my 3 unknowns. And if you do have 3 unknowns, you are going to need 3 equations to find a unique answer, if indeed these do intersect at a single point. I've labeled my rows R1, R2, and R sub 3, and so I can use some footnotes as I go along and track what I'm doing, because if I do make one of those small mistakes, if I sort of make notations of how I worked out the problem, it'll be easier to find my mistake if I find at the end that I've made one. So the first thing we're going to do, with the z-value having a coefficient of 1, I feel like it's going to be easiest when I combine these equations to get rid of my z variable first. Some textbooks, and it's not a bad idea, will try and get you to get this pattern where it steps down and your last variable that you have in your third equation is going to be z, and you solve for that. It really does not matter which, at least as far as I'm going to teach it, which variable you get rid of first. We just need to whittle down to a 2 by 2 system, and then finally, in your next step, find a single variable. So at any rate, we're going to do row 1, and these are both have the same sign, so I'm going to multiply the next one by a -2. So it's going to be row 1 plus -2 times row 2. So row 1 plus -2 times row 2. So row 1 is going to be, well, it's going to stay the same, so it's going to be 2x plus y minus 2z equals -1. I'm going to take row 2 and multiply it by -2 and get 4 times -2 is -8x. -2 times -2 is positive 4. And -2 times -1 is positive 2z. And that's equal to then -10. So I've created an opposite coefficient in front of the variable that I feel is going to be easiest to get rid of first. So I'm going to add these, and I forgot my y already. So I'm going to add these and get 2 minus 8 is -6x. 1 plus 4 is going to be 5y. And -2 and positive 2 on the z variable is going to cancel out and end up with just equals -11. And good. So now I'm going to do that step, and I just combined these two together. So we're going to do a second step and combine the second and third equations. So remember, we need to add 2 different pair of equations from the original 3 to make our new system of 2 equations and 2 unknowns. So now I've already got my signs that are opposite. I just need to have a -3 here, so it'll cancel out with that +3 when I add them. So I'm going to do 3 times row 2 plus, and that'll give me my -3 here. I've got a +3 to cancel out, so I'm going to leave row 3 alone and do 3 times row 2 plus row 3. A little short on the space there. So 3r, so 3 times 4 is 12x. And 3 times -2 is -6, y. And 3 times -1 is -3z. And then 3 times 5 is equal to 15. My second equation, or my second line here, is going to be row 3, and I'm going to leave that alone. So I'm just going to have 1x minus 2y, positive 3z, and equals 6. And now we're going to add those equations together. Whoops. So I have 12 and 1 makes 13x. -6 and -2 makes -8y. This cancels out. The -3 and 3z cancel out, and we get equals 15 and 6, which is 21. Good. Now, these 2 equations are going to set up the second step that I talked about, which is I've just added 2 pair of different equations, basically first and second and third. And now I've got this in step 2, I have this 2 by 2 equation, basically. 2 equations and 2 unknowns. So I have, this is like my step 2, I have negative 6x plus 5y equals negative 11, and 13x minus 8y is equal to 21. So now I want to solve this linear system. So what do we want to get rid of first? It's really your choice. My y values already have opposite signs in front of them, so I'm going to come through here and multiply. Well, let's rename these. Let's say this is row 1 again and row 2 for my second step of my equation. So I'm going to make these opposites. My lowest common multiple is 40. So we're going to multiply this by 8 and this by 5. So we're going to do 8 times row 1, which is going to make that a positive 40, plus 5 times row 2, which is going to make that negative 40. And let's see what happens. 8 times negative 6 is negative 48x. 8 times 5 is 40. And 8 times negative 11 is negative 88. And now we got 5 times row 2. So 5 times 10 is 50. Another 15 is 65x. And 5 times negative 8 is negative 40y. And 5 times 21 is, 5 times 20 is 100, so it's 105. I've got my opposite numbers that I need. So we're going to go ahead and add those together. This is going to be equal to negative 13x. This is going to cancel out. And 100 minus 80 is 20. So 105 minus 80 is 25. And 25 minus 8, let's see, 25 minus 8 is going to be equal to 17. And I believe I did this incorrectly. Let's try that again. We have 65 minus 40 is 25, and 25 minus 8, yes, I did make a sign error there, or a mistake. Easy to make, especially now I'm talking to you and doing math at the same time. So let's try that again. Positive 65 minus 48, 65 minus 40 is 25, and minus 8 is 17. So now we have 17x equals 17. Sorry about the little mind fart there, brain fart. Divide both sides by 17 and you get x is equal to 1. So I found my first solution, my first of my 3 unknown variables. So we're going to take this value of x now, and my direction said start back substituting to solve for the remaining unknown variables. And start with the 2-variable equation and then finish with the third 3-variable equation. So I'm going to plug this x value into one of these equations. It doesn't matter which one if we actually have a true solution. So we're going to take, I don't know. Let's take the second one here so I have fewer negatives to deal with. So our third step, we're going to start back substituting. So let's get a different color here. How about orange? So this x is going to go into the second equation. Again, you can pick either one you like. And we have 13 times our x value of 1 minus 8y equals 21. So 13 times 1 is, of course, 13. So we're going to subtract both sides by 13. Get negative 8y equals, now 21 minus 10, I'm going to go a little slower this time. 21 minus 10 is 11, and 11 minus 3 is equal to 8. So we're going to divide both sides by negative 8, and get y is equal to negative 1. And I'm starting to run out of space, so instead of writing this in, let me get this erased and show you the last substitution to find the remaining variable of z, and then we'll check our answer. So we got the board cleaned up here, and our 2 values we found so far are x equals 1 and y equals negative 1. So we're going to take these values, plug it into any of these 3 equations we like. Let's pick the one, let's just do the first one. So we have 2 times 1 for the x value that we just found, plus the y value that we just found of negative 1, and then minus 2z equals negative 1. So we have 2 times 1 is 2, minus 1 minus 2z equals negative 1. This is now going to be 1 minus 2z equals negative 1. Subtract both sides by negative 1, or subtract both sides by 1. We get negative 2z equals negative 2, and z is equal to positive 1. So we have our third solution of z equals 1. Now, you need to check your work to make sure these are right. Whether that is putting them into your graphing calculator. If you have maybe a CAS calculator, you can just type in this three-way system of equations, linear equations, and just ask it to solve it for you. Or you're going to manually put those back in, and we've got 2 times 1 plus negative 1 minus 2 times 1, and make sure that that equals negative 1. Now, it won't be enough to just check one of the equations. You have to check all three if you're doing this manually. So 4 times 1 minus 2 times y minus z, and make sure that's equal to 5. And then finally, our last equation, which is x, which we found again to be 1, minus 2 times y plus 3 times what we found to be z equals 6. And 2 minus 1 is 1. Minus 2 is negative 1. This is 4 plus 2 is 6. 6 minus 1 is 5. And then 1 plus 2 is 3. Plus another 3 is equal to 6. And we've checked our solutions. Let's do one more example to make sure that you really got this down. Example number 2. We got 2x plus 2y plus 5z equals 20. Y minus 4z is equal to negative 16. And 3x minus 2y plus 9z is equal to 36. Would you like to try and do this before we finish the example? Okay, now our second equation here does not have an x in it, so let's not worry about that too much. It's not going to change the process. We're still going to add 2 different pair of equations to get it down to a 2 by 2 system. Solve that linear system, 2 by 2 system, by substitution or linear combination, however you like, and then start back substitution. So we can't get rid of the x's. If we add the first 2 and the second and third one, there is no x, so we're not going to be able to eliminate that. So we're going to try and get rid of the y's first. So I'm going to make sure I follow my notes here in case I make a silly mistake. Okay, we're going to take over here and do, well, I'm going to get rid of the y's first. Now the positive 2, I need a negative 2 to show up. So I'm going to take the first row and take the second one and multiply it by negative 2. And we're going to add those together. I already have a positive 2. I want this y to have a negative 2 in front of it. So we've got 2x plus 2y plus 5z equals 20. And multiplying the next equation by negative 2, we're going to have negative 2y plus 8z, and negative 2 times, I didn't show you I was doing that. Negative 2 times 1 is negative 2. Negative 2 times negative 4 is positive 8. And negative 2 times negative 16 is 32. Now we're going to add those together and get 2x, 13z equals 52. And that'll be one of our equations we work with in just a second. Over here, I'm going to take the second and third equations, and I've already got a negative 2, so I want this to be positive 2. So we're going to do, let's see, 2 times row 2 plus row 3. So that's going to be 2 times row 2 is going to be 2y minus 8z equals negative 32. Now we're going to take the third one and leave that alone because we already have a negative 2, which will match up with the positive 2 here in front of this y, and get 3x minus 2y plus 9z equals 36. And now we're going to add those equations together and get 3x. The y's cancel out. Negative 8 and 9 is positive 1z. And then 36 minus 32 is equal to 4. So we're going to bring these together and have a 2 by 2 equation. So we'll have 2x plus 13z equals 52, and 3x plus 1z equals 4. Like the way that looks. Okay, so now we're going to solve this systems of equation. Let me just make sure I haven't made any mistakes here. 2, 13, and 52, and 3, 1, and 4. Good. Now, we are going to solve this for, just something. It doesn't matter if you solve for the x first or the z. If I solve for z, though, I got a positive 13 and a positive 1. So I only have to change one of the equations if I decide to get rid of the z's first and solve for x. So I'm going to multiply the second equation here by, and I'm going to kind of shortcut this just a tiny bit with the notation. I'm going to multiply this by negative 13. And we're going to have 2x, let's pick a different color for our scratch work here though. Let's take a green, blue, how about yellow? So we have 2x plus 13z equals 52, and this is going to be what? 39, negative 39x, negative 13z, there's the opposites we want in front of one of the two variables, so it cancels out. And 40 and 12 is 52. So we have negative 52. So when we add these, we have negative 37x so yes, negative 37x equals, the z's cancel out, and actually so do the 52. So we get that negative 37x equals 0, so x is equal to 0 itself, because when you divide both sides by 37 to get the x alone, you're going to have an answer of 0. Now that we have one of our solutions, we start our back substitution process, and let's take this value of 0, plug it into one of the two original problems for z, and since this has a 1 in front of it, that's going to save a little bit of work, so I'm going to do my back substitution, plugging my 0 in for this x value. We get 3 times 0 for x plus z equals 4. 3 times 0 is equal to 0, so our z value ends up being 4. So I have x equals 0, I have z equals 4, and now I need to do one more back substitution to find my last remaining answer. So we're going to take, well, what's left? We have to find out what y is. So I can take the x value of 0 and plug it in here, the z value of 4 and plug it in here and find out what y is equal to. Or I could just simply use this equation. I can take these values and plug them into any of those equations I like. And this one's the shortest, so let's do this. So we're going to take our last step of back substitution is going to be y minus 4 times the z value that we just found of also 4 equals negative 16. So we get y minus 16 equals negative 16. Add 16 to both sides. And y is equal to 0. So I'm not going to check this again like I did the last one. You should be able to do that now. You take the values of x equals 0, y equals 0, and z equals 4. And that is the three-dimensional point where these three planes intersect. I showed you that diagram in the introduction to this video. So there's your two examples of finding the solution to a system of linear equations where there's three unknowns and there's one unique solution. We'll have another video coming up where there's an infinite number of solutions and where it's inconsistent or no solution. I'm Mr. Tarut. Go do your homework.